Yes, your co-host.
Yeah.
I think you can you share your desktop as a co-host? I think so.
Yeah. Yeah. I can
Yeah,
share my screen.
then it's fine. That's fine. All right, that's good. So just requesting to Humayun to the Harwell backend tech support person, don't make me host, okay? Because I won't be available all throughout the time. So make either Rehab a host or even Sakib a host if you need some backup. Okay, so yes, yeah, Eda is also here. Good to see you all here. Yeah, I'll say let's start.
Yeah. Okay. Sure. Okay. Can everyone see my screen?
Yes.
Okay. Okay.
Yes.
Thank you. Okay. So yeah. Welcome everyone to the Harwell Datathon 2022 workshop day 7. I'm today's instructor. My name is Mohammad Saqib Hassan. I'm currently a PhD student in computer science at Stony Brook University in New York. I'm originally come from the country Bangladesh, where I was a research engineer there at Bangladesh University of Engineering and Technology, which was also my bachelor's alumni university. So yeah, I'm done bragging about myself. So let me start off with today's workshop, day 7. We will be this will be the second workshop on machine learning specifically, and today we'll be discussing 3 important algorithms: decision tree, which previously Tanzim has talked about during workshop 6 and workshop 5 a bit, and we'll be focusing on the ensemble versions of decision trees, random forest, and boosting. So just to tell you, I'll be going through the slides and I'll be also going through some demos. If at any point you have anyone has any questions about it, please let me know. Please just unmute and let me know. Okay, and I'll periodically check the chats as well after a few slides. If you have any questions, just let me know in the slides. All right, so we can begin. 1 minute. Okay. So yeah, the outline would be of today's lesson workshop would basically be, I'll start with decision tree. I'll give a brief introduction, state some of the metrics that are used for creating a decision tree, and then I'll go through a hands-on example of how these metrics are used to create a decision tree. And afterwards, I'll be focusing on the ensemble methods of decision trees, which are basically the random forest and the gradient boosting. And then there will be 2 code demos. The first code demo will be on Pandas and Numpy, and the second code demo will be on Kaggle about basic machine learning. Okay, so what is an AI and ML? So during my undergraduate, one of the lecturers, when she came in to the class, she just told us all that AI is just a glorified way of saying that we are using a bunch of if-else statements. I was visibly shocked. I never had an ML or AI course before that, and I didn't buy her statement. So then she said that if you look at decision trees, you'll find the proof that it is actually a bunch of if-else statements. So why is it so? So let's just look at here. So suppose we have a data set here. So it's basically a data set that depicts the age, mileage, and road test, whether a vehicle is road tested or not. And based on that, it suggests whether this vehicle should be bought or shouldn't be bought. So suppose a decision tree that can be created from this data set is basically this. So basically, if you see the road tested feature, then you can determine, like if it is road tested, then you can buy it, or if it is not, then you don't need to buy it. Now this is how you have seen you've had some lessons on decision trees. So this is basically how a decision tree would look like or operate. Now I just wrote a Python function here, and it's basically doing the same thing as a using if else. Like when the data we get the data, if you just check the road tested variable of the data class object, and if it is yes, then you return by, else not return by. So I just did the whole ML thing using a bunch of if else. So why not just why do we do this, all this model, this training, this loss function, and etc. Instead of doing this, we just write a bunch of if else statements in a file and then just run it. Now, why shouldn't we do ML using if else? Now this is a very small and a very easy data set, but when you have data sets which are quite large with thousands of features, if you're gonna write an if bunch of if else, it will be like thousands and thousands of looped or nested if else says, more than the number of nested if else that you have done during like some of the exercise during if statement exercises during your beginner programming course. Most probably you have done only three nested if else, but here there will be thousands. So that is why we don't do ML using if else. We use do it using by learning some functions, loss functions on the data set. So yeah, fun aside, let's actually start with our today's lesson. So I'll begin. So let's start with decision trees. So you have worked, most of you have worked out with decision trees already, even those who haven't coded a single ML algorithm or an ML program. How? Because decision trees has multiple meanings. It has some meaning in statistics. It has some meaning in machine learning model. So previously, I'm pretty sure a lot of you have learned about decision trees, that it's a sort of a tree-based visualization where there are nodes and vertices, and at each node, a condition on a variable is tested, and based on that, an action is taken, which is determined by the vertex. So yeah, it's this type of decision trees, this visualization is used a lot in the finance sector. It's used a lot in statistics and probabilities. You've probably used decision trees mainly in your probability class. You called it probability tree, and it was just 90 degrees rotated, much like this. So yeah, the decision tree that's happening is here. I'm talking about is, suppose it's like this. Here at each node, you have a condition, and based on that condition, you have pathways, events that where you will go, and these events or outcomes are determined by each vertex. Each vertex determines a path. So yeah, this is basically a sort of a visualization of the possible decisions that can be taken, and this is probably you all are familiar with. This is a probability tree. You've done it with for a bunch of problems in high school, such as taking whether taking a red ball or a blue ball from a bag and then returning it, and see how the picking another red or blue ball and see how the probability changes, or the probability branches, etc., or not returning the ball and see how it changes. So yeah, this is also a sort of a decision tree. It's the only difference being that it's 90-degree rotated. So in ML, decision tree looks the same. It's almost the same to this, but in there it's it's considered a supervised algorithm or model. So in decision tree in ML is basically it's a supervised algorithm or model that takes in the input output data pairs and then converts them into a sort of a decision tree like we have previously seen. And here at each node, a feature of the original input data is tested, and based on the values, we move to the next node. So many a times you'll see that it's not, you'll see something that's mentioned like cart algorithm. This is basically classification and regression tree, and it's the same thing as a decision tree. So here we have suppose a data set, and we have the corresponding decision tree that's constructed from this data set in order to classify based on outlook, temperature, humidity, and windy, these 4 features, whether the person will play golf or not. So let me discuss a bit about some of the components that exist in a decision tree model. So at the very first, you have the root node. So the root node is the very first node of the decision tree, or the top node, and it determines the name of the root node determines which is the very first or the most important feature on which you decide first. So in the case of this data set, it's outlook, and you can see that 3 vertices are coming out from this node, denoting the 3 possible outcomes or the values from this node. So it can either be sunny, overcast, or rainy. Then there's something called the leaf node. The leaf node basically is the answer to your classification problem, or the final goal, answer to your final goal. So in this case, our goal is to predict whether we'll golf or not. And there are 2 possible values, yes and no. So a leaf value is something like this. So it's basically shown using boxes when representing decision trees. So, and it determines what will be the final outcome or the output goal. So here, suppose if the outlook feature is overcast, then definitely it will be you should golf. Now there's something called the inner nodes as well. Basically you can't define. It is sometimes possible, but in many cases it's not possible that you can divide a whole data set using just the root node. You will need other nodes as well, as in you will need to analyze other features as well. So the inner nodes are basically the nodes which are below the root node, which are other features which are used to like basically dissect or split the data set. And at the very end of the decision tree, at the very bottom, every of the values will be leaf nodes, because basically at the bottom you'll have the answer. So this is how the overall structure of a decision tree looks like. So now the question is, how is
What were the vertices?
Okay. So the vertices are basically, as I discussed, like the vertices determine the outcome from each node. Like suppose outlook, you have the sunny, overcast, and rain. Suppose when you're analyzing humidity, when you're dividing based on the humidity feature, so humidity has only 2 options, normal or high. So there will be 2 possible vertices. So if it's normal, then it will go a different path. If it's high, it will go a different path. Am I clear?
So yes, no is the leaf node and humidity is the inner node.
Yeah, exactly.
And the vertices is the way it's going.
Yeah, exactly.
Okay.
Basically, the inner node, whatever it's a feature, right? So this feature can have multiple values. So the vertices determine which consecutive path will be taken based on the feature value. Based
Okay,
on the
thank
value of
you.
the feature. You're welcome. Okay, great. Yeah, I welcome this type of participation because it's in a Zoom meeting. We don't have the same feedback as like conducting an in-person class. So please ask away. So yeah, so this tree, this tree is not constructed out of the blue. This tree is learned, or so you've done some basic machine learning about about some theories of machine learning in the previous workshops. You know that machine learning is basically the machine learning algorithms or models try to take in the data and try to learn the representation between the input and output. So this decision tree is also a representation between the input features and the output class. So this has to be learned from data. Now we can't just make this decision tree out of the blue. So so how is this tree learned? Now the first thing is any decision tree algorithm or decision tree model, it tries to find the smallest and shortest possible tree to classify the data set. You've previously seen that when in case of overcast, it simply says it's yes. So it tries to optimize. Like it could test other variable, other features as well, but it didn't because according to the data, it's not necessary. If it's overcast, then it's always yes. So similarly, what I'm saying is that the decision tree tries to learn to find the smallest and shortest possible tree to classify the data set. And now how can it do it? Now this is a sort of optimization or a sort of like maximizing your resources to a certain extent by minimizing the number of how do I put this? Minimizing your error or use. So in decision tree, this optimization or this learning occurs by it will select the most discriminative feature at each level or node. So let's look at through the example again. So here we have that age, mileage, and road tested data set. So previously I've shown this this decision tree. It basically uses the road tested feature to classify. It doesn't need to look at the other features at all because the road tested feature is enough. Now suppose I have this this decision tree. Now this decision tree, what it does is that it first looks at the age, and based on age, it can't actually fully dissect whether it should. It can say that if it's always old, then don't buy. But if it's recent, it can't actually say whether the car should be bought or not, the vehicle should be bought or not. So it looks at the next feature. And basically in the next feature, you have low and you have another, you have low and high. Now, basically, if it's low, yeah, you should buy it. But if it's high, then it's not sure whether it should be bought, the vehicle should be bought or not. And then we come at road test. And based on road test, you do the final calculation. So what's the difference between this and this? Isn't this decision tree a bit clumsier? Like it's doing a lot of unnecessary calculations, which are not necessary. And this decision tree, isn't this a smaller and shorter tree that uses the that has the least amount of calculations needed to find the answer? And also, don't you feel that road tested is a more discriminative feature than age or mileage? Like basically using age or mileage, you can't fully dissect whether you should buy or not, but road tested itself is enough. So a decision tree optimization algorithm or a decision tree will learn a sort of tree like this instead of a tree like this based on the data set, which will have the shortest and smallest possible tree. So now the question arrives, this optimization, I said that selecting the most discriminative feature at each level. So how will this happen? Now, there are a number of ways that we can select these features at each
I'm
level
sorry,
of.
can
Oh, sorry.
I ask
Yes.
a quick question on the prior slide?
Yes. Sure.
On your model, why isn't mileage high specified before the X variable
that's-
selected?
Sure.
No, I'm just curious.
No, it's actually a type.
Oh, okay. Thank you so much.
It's actually a type. Okay. Yeah. So, okay. Moving on. So, how do we select these features? Now, there are a number of ways we can select these features at each level. You'll find a number of methods. Now, the two most common methods are information gained by entropy. It's sometimes called the Id3 algorithm, and the other is the Genie Index. Now, information gained by entropy, you'll see that this has already been referred to in workshop 6B and also has been discussed by Tanzim. I'll be repeating basically that problem again here in a bit of more details. So yeah, these are two most popular ways of selecting the most discriminating features. So what's information gain? So information gain is basically a metric that tries to calculate how much information is gained when we select an attribute using what is commonly referred to as the Shannon or information entropy. Like you have heard about the normal entropy that's used in the chemical sciences specifically. This is quite different from the entropy that's used in computer science, which we call as information or Shannon entropy. And the formula for this is basically this, that suppose you have from 1 to C different values, and each value has a certain probability attached to it. Then the entropy of that whole probability distribution or all the possible classes would basically be pi into log base 2 pi, the summation of the negative summation. So this is basically the entropy. I'll discuss the significance of this entropy in the following slides and why this works or how this works, etc. So yeah, and another thing that's another metric that's used for selecting the attribute is called the Genie Index. So this Genie Index is basically this, which is basically 1 minus summation of the square of all the probabilities of all the probabilities of all the possible output classes. So this is the Genie Index. So what it does is that the Genie Index is calculated and we select the attribute based on the lowest value of the Genie Index. So we'll discuss about Genie Index at the very end of the decision tree slide. So yeah, okay. So now let us solve a problem. Let's do a hands-on problem to see how these metrics work in creating and constructing a tree. Okay. So any questions till now? Anyone? Okay. So let me continue. So as I discussed, what is entropy? Now this information Shannon entropy or information entropy, this is a measure of the randomness or uncertainty of a variable given its probability distribution. Does anyone here not know what a probability distribution is? Okay, so I'm assuming everyone knows. So yes, it measures.
Rakib,
Yes.
just a second.
I think you should still explain a little bit about probability distribution, because I'm pretty much
Okay.
sure that some people are shy and they don't want to ask because
Okay.
they might, yeah, just explain it so that everybody also
Okay.
who knows, they can also have a review.
Oh, okay. So suppose probability distribution. Suppose you want to Jack. So Jack wants to have ice cream. So there are two possible choices of having ice cream. So whether he will have, whether you will have the ice cream, yes, or whether he won't. And similarly, the suppose we have Jill. We want to we have the probability of Jill having ice cream. So this is also can be a yes no answer. Now Jack having ice cream and Jill having ice cream, these are two different variables, and these variables can have, each of these variables can have two possible values. And now we are not sure what are the two possible we only know one thing. What is the probability of the each of the, what is the probability of the variables? Like for example, for Jack, him saying yes is a probability of 0.1, and him saying no is a probability of 0.9. But for Jill, it's the probability is equal. It is like 0.5 and 0.5 both. So this is basically a probability distribution. So basically you have a variable and its possible values are there, and the probability for each of the possible values are given. Now, how does this come into machine learning? Like in machine learning, when you have an output, there can be multiple classes. We are usually working with binary classes. Suppose like this is a binary class. So in binary classes, you will have either a yes or a no, or a 0 or a 1. And you will not, and the 0 and 1, you'll not be like 100% sure. It will be basically a probability value, like 90% sure it's 1 and 10% sure it's 0, or it's like 50% sure it's 1 or 0. So that is why machine learning probability distribution comes in, because when the output class, you deal with the output class, you have to deal with a probability distribution. In many cases, it's not an absolute. So yeah, this is basically what a probability distribution is. So this entropy, it tries to measure the randomness or uncertainty of a variable given its probability distribution. So we have the probability distribution of Jack and Jill. So we can calculate the entropy using this formula. So suppose we have this probability distribution. So the probability entropy here would be minus 0.1, would be log base 2, 0.1, and 0.9 into log base 2, 0.9. And the value that comes is 0.47. And if we do the same for this probability distribution, the entropy would amount to 1. Now, what's the significance of this value? A higher entropy usually indicates that we have more uncertainty, or means we cannot derive more information from a probability. Now, how do I give this? Let me give you an intuition about this. Suppose you have in this probability distribution, you can see a stark difference between the two classes, and you can see that the chances of no are very much higher than the chances of yes, right? So there's less randomness or less uncertainty here. It's probably going to be, the answer of Jack having ice cream is probably going to be no, more or less, we're sure. But in the case of Jill, you can say that we are a bit confused. It's not certain whether she will say yes or no, because we're not because the probability distribution is such that they are very close to each other. So in this case, the uncertainty or the entropy would be higher. So in this way, the entropy is a sort of like measuring how symmetric or uniform the probability distribution is. A uniform probability distribution means we are uncertain about what value the variable will take, whereas an uneven or one value having a very high probability means that we're pretty certain it will take the variable will take that value. So yeah, this is basically entropy. Any questions? Okay, moving on. So next we have information gain. So information gain is basically another metric. It is basically the amount of decrease in entropy when a certain feature or attribute is selected. Suppose you calculate the entropy of the whole data set, okay, without considering any of the features. And then you consider one feature whose value is fixed. You would see a change in the overall entropy. And this difference is basically called the information gain, because as you are decreasing the entropy by selecting a feature or attribute, you are what you're doing is that you're decreasing the uncertainty in the overall analysis of the data set. So you're gaining more information. So this is the formula for information gain. So entropy of Y is the output class, and the output class given we are conditioning on a single input feature. I believe that you have learned a bit about condition probabilities in the previous lectures. So if you don't get it now, no problem. We'll see an implementation of this in the following slides, and you'll be more clear about the things, these things. Okay. Okay. So next, okay. Now I want to look at the Id3 algorithm first, which uses entropy and information gain, and I'll look into the Genie Index algorithms later on. So first, let's look at the Id3 algorithm. So this is a data set. This is the very common data set. This is Tanzim has like shown the Id3 algorithm on this data set in this previous workshop. So I'm using this one as well. This is the play tennis example. It's one of the most popular and common examples data sets that's used for explaining decision trees. And now I will be and this whole thing is the decision tree that is created from this data set. Now, in the interest of time, and because as you'll be implementing machine learning models for your datathon, you don't really need to have the exact, you don't need to go from scratch or have the exact theoretical knowledge needed. You just need to know that how the model works from an abstract level. We'll just be looking at how the root node is constructed. And I'll later state how this is these constructions, these subtree constructions are basically a recursive process. So I'll just show how using entropy and information gain, why instead of temperature, humidity, and windy, the root node outlook feature is selected. Now, first, let us look at the Id3 algorithm. So without we look at the source as in the output class. So we don't look at any of these features now. So suppose the probability of playing tennis is 9/14, and the probability of not playing it's 5/14. So you can basically this is calculated using this. There are 14 values, and this is calculated. And now you can calculate the entropy of this column, or the play tennis column, or the output column, basically using this formula. So it's minus 0.642, the probability of playing into log2 of probability playing. And then you have the probability of not playing to log2 of probability not playing. And the entropy value, it comes out as 0.940. Okay. So first, if you remember the information gain formula, you need to calculate the y. Y is basically the output class, column, or feature. You need to calculate the entropy of this at the very first. And then you need to calculate the entropy based on conditioned on a feature variable, one of the features. So we're done with the first part. Now let's do the second. Now we are going to be conditioning play tennis or the output class based on the possible based on outlook. Now outlook has sunny, overcast, and rainy, 3 possible values. Okay, so we are going to be calculating, conditioning them on these values. Like, what's the value of play tennis given sunny? What's the value of play tennis given rainy? What's the value of play tennis given overcast? So yes, as you can see, that probability of playing given sunny, we're just going to this is going to be this is a conditional probability, and not playing sunny, this is basically 1 minus this. So yeah, and then we are going to be calculating the entropy of just this conditional probability distribution. Okay, so we are finding the entropy of source given excuse me, yes, so we're going to be finding the entropy of source given sun. So this is repeated for overcast and rain as well. So the probability of playing given overcast, it's actually 1. There are actually 4 cases of overcast, and it's always they're going to play. So not playing is 0. And in this case, the entropy is 0. Why? As I told you, like if the probability distribution is very skewed, then the entropy is very low. In this case, only one class is important. The other class, it never happens in this condition. So the entropy is 0. And this is done for rain. This is the conditional probability. There are 5 rows where the it's rainy. So based on that, they calculate the entropy. So now we have 3 different entropy variables based on 3 different possible values of output. Now we will be calculating the final entropy, which is basically the entropy of play tennis given output. Now, how this is done? This is done using weights. Like there are 14 different rows. 5 of them belong to sunny, 4 of them belong to overcast, and 5 of them belong to rain. So basically they're going to be doing a weighted sum. So basically it's going to multiply this entropy with 5 by 14. It's going to be multiplying this entropy with 4 by 14, and this entropy with 5 by 14, because as I said, the values are divided as such. And in this way, you have what's called 0.69. Your value is 0.69. Okay, so when we condition, you can see that when we condition on the outlook value, the entropy or the uncertainty of the data is sort of decreasing, right? So now we will calculate the information gain when we consider the output. So information gain of play tennis when we consider the output is basically we have the entropy of play tennis, and now we have the entropy of play tennis given we are conditioned on the output. So 0.94 minus 0.69, 0.25. So our entropy is decreasing by 0.25, and this is the gain that we have. or the information gain that we have. So this is the reduction part. Now we have done this for one feature, which is basically the play tennis given out. So in the same way, we'll be calculating it for the other three features: temperature, humidity, and wind. So we'll be doing the same thing. There are three possible values here. We'll be dividing the data sets such like that and calculating the same way. So yeah. So then we will be calculating the information gain. So without going, yes,
maybe I'm lost a bit. I'm so sorry, but
yes,
I
yes,
didn't.
sure.
Can you tell me what's the work behind IG play tennis by temperature?
Okay.
Can
Okay.
you tell me what's the work behind that? Okay.
Okay. The information gain, IG is information gain. So suppose in Outlook, what we have done, we have the three possible values, right? Three sunny, overcast, and rainy. And so we calculate, we divide the data set such that we only consider the sunny, because we consider the overcast, and we only consider the rainy. And based on this, we calculate the conditional probability. So we'll just, like for sunny, there are only 5 rows. So we'll be considering only those 5 rows, and we'll be then calculating the probability of playing and not playing. And
Yes,
after we're done with this, yeah.
Okay.
So, okay. So basically this is Outlook. So for temperature, we have hot, mild, and cold. So just like sunny, overcast, and rain, it will be like probability of playing given hot, probability of not playing given hot. So similar probability of playing given mild, probability of not playing given mild. On probability of playing given cold, probability of not playing given cold. Okay. So, and then we'll be calculating the entropy for each of these, like the source or play tennis given given the features value. Okay. And then we'll have a final entropy, which is probability of play tennis given temperature. And this, suppose for hot, we have 1, 2, 3,
5.
4. Are you sure 5 or 4?
No, 4. That's 4.
Okay. Okay, 4. So we have four different out of the 14 values, 4 different values belong to hot. So it would be, the weight would be 4 by 14 for the hot.
In the
And
middle,
for,
maybe. Yes.
Yeah. Oh no, this is for the Outlook. Like the I'm talking about another. So like the value that you will have for like source given hot, you would multiply it with 4 by 14. So for mild, it would be 1, 2, 3, 4, 5, 6. You have 6 values. So you would be calculating for 6 by 14. You'd be multiplying the entropy of source given suppose mild. You'd be calculating for 6 by 4 and etc. So you'd be like basically doing a weighted sum. So this is repeated for temperature. Is it clear? Yes.
I just wanted to say one thing. Girls, you remember my last slide? Because there was also, so you were wondering that, so the thing is what Sakib is saying, it's exactly what I said in my last slide. So if you have the formula in front of you, maybe on a separate browser, you can see that if one of those attributes of every feature, so the features are the columns except for play tennis, that is our class which we want to classify. So for every feature we have different attributes, and if all of those attributes are classifying for yes, then the probability, I mean, the log of that, it just becomes automatically 0. So and if it's equally distributed, then it's 1 divided by the number of observations. So if you're wondering about 0 or equal distribution, it's you have to just, these are like 2 additions on that formula. You can just keep it on the separate browser. it's all on the Google Drive, then you can probably see the calculation, how it's going. And I will also suggest you to take out your calculator and
Yes,
and
I'm
tip it
doing
down.
it.
Exactly. So it's an elaborate version of what I introduced last time. It's very funny, actually. It's interesting. Once you get the idea of it, once you get the
Yeah,
hang of it, you
it's
will just
interesting,
love
but
it.
the thing is, so many things it's all together, so it's just blurring out. I got the last
Yeah.
slide and it's blurring out the last slide. So there's so many informations coming in and going out. So that's why.
Okay.
Sorry.
No,
I would.
take your time. Take your time. Take your time.
Yeah, I would say that. Yeah. Basically, I looked at decision trees at the very first time during my fourth year AI course, and yeah, when the professor was going through the slides of the decision trees, most of us were sleeping because we were lost after like 5 or 10 minutes. So it's not a big issue if you are lost at the very first time. I have been taught decision trees in basically three different courses using this same example. And even then, like if I'm given a pen and paper and told to do it from scratch, I might not be able to do it perfectly at first. So it's all right that if you're taking it up, like I'll give a link. Basically, I'll give a link that goes. I'm just going through only the root node. Okay, so there will be the other nodes as well. So that video link, you can go through that. So basically, we are not going through that because of the interest of time and like not to have your head jam at all for this, because you'll not be implementing the algorithms from scratch for the data farm. But
I wanted to ask if there's
yeah.
a typo and the last copy platonist given outlook. Is there any typo? There's a 5 by 14, 4 by 14, and there should be 6 by 14.
5 plus 4, 9. No, it will be a 5 by 14.
No, it's exactly correct, because you see, we have 14 observations, we have 14 instances. So if you look at
Sorry.
If you look at the denominator, so it's like, and the numerator, so you have 14.
Yeah, it's okay.
And then you have 5 plus 4 plus 5 is 14. It is.
Yeah.
Oh, my test result came. Let me see if I can fly tomorrow to USA.
Okay. So yeah. Okay. Moving on. So we have the, like basically in this similar manner, you'll be calculating the information gain when conditioned on temperature, humidity, and windy. And then you'll be selecting the feature which has the highest information gain, because you should say it's the most discriminative feature. This this information gain value is shown. So since outlook IG is the highest, you'll be selecting IG outlook, and it will be the very first root node. Now,
I just had a quick question about
sure.
what do you call that output? It's not 25%. What is it called?
It's an information grain. It's not actually an output. It's actually a metric. It's a measurement. Like when you are conditioning on the outlook, or when you are selecting this feature, how much information are you gaining, or how much uncertainty is decreasing? Like entropy is a measurement of the uncertainty. So definitely when you're conditioning on that feature, the entropy is decreasing, like your uncertainty is decreasing. So how much is that decrease? This is the information gain.
Can you please show the formula of the information gain once again, so that it's clear again?
Yeah.
So okay, so it's can you go back one step? The formula for entropy, the E.
Yeah. Okay.
Exactly.
Yeah.
So there you go. This is the E that you can see everywhere. See, that's like the probability distribution that Saqib explained, and I also explained in the last class. So that's the entropy, what he just talked about. And Saqib, if you can go up to, yeah, exactly. So the E here is the entropy. So EY given X means the entropy of one feature given these conditions X, like entropy of outlook given the condition, is it rainy or sunny or something. And then you have the EY on the left, on the first term of the right-hand side. That's your total entropy of the main target class, the yes and no, which is we already calculated, that is 0.94. And then you have the information gain on the left-hand side. So you always deduce the entropy of every feature given every attribute from the main entropy, from the altogether, from the main, the 0.94. So if you go up ahead a couple of slides where you have the calculation, Saqib. Yeah, so exactly. So what these are just replacing the formula and just putting it, it's just counting. You're just counting observations.
Yeah, as Tanzim mentioned, yeah, we are basically replacing the formulas and count. So we have done this for the root node. Now for the other nodes, suppose we have only done this for, so for these portions, it would be you would be doing the same algorithm as well, except you don't need to consider outlook at all. You'll be considering the three data, only the these three features, and for suppose after you have traveled to this branch, you'd only be considering the data points where outlook is sun. And here, if you go down this branch, you do this same calculation and you would be considering the values, the data rows where outlook is rain. Okay, so yeah, this is the this is basically rinse and repeat. So Id3 algorithm, this is further down by dividing the root node and doing the same calculations. We'll do this till there are nothing but leaf nodes. So one thing is that implementing this Id3 algorithm from scratch, this is not a part of our datathon. So you don't need to worry about this a lot. Like, this is not an AI exam, so we're not going to test you on how fast you can do this in a written exam. There are libraries that simply implement this. You just need to mention, I want the Id3 algorithm, or I want the Genie Index algorithm, etc. So since in the interest of time, and since we want to stick to relevancy, we just showed the very first step. If any of you are interested into seeing how this whole tree is formed, then you can see this following link. It's about 30 minutes and it goes step by step over each of the features in much more details. And yeah, it explains the whole process. Okay. And now on to Genie Index and Genie Gain. So the Genie Index is basically this whole problem of Id3. We can solve it in a similar way if we just replace Genie Index with entropy, the Genie Index formula with the entropy formula. So what's Genie Index? So Genie Index is, it tries to calculate the amount of probability for a specific feature. If the probability of a feature, when we select a feature, how incorrect is it going to be when selected randomly? So like suppose, how do I put this? We can go to, okay. The formula is 1 minus addition of all the square of the probabilities. So it varies between 0 and 1. So, okay. I think, yeah, this statement should clear it up a bit. So if the Genie Index is 0, it means it means that all the elements, when we consider that feature, it belongs to one specific class. Like, for example, during the summation, like if all the values for when we consider a single feature, if the probability is 1 for playing and probability is 0 for not playing, then what does that mean? When we consider that feature, we're there's actually no chance of being incorrect. You probably know that it's always going to be playing, So yeah, we take that. However, yeah, let me go here. So yeah, suppose we have the probability of playing given overcast and probability of not playing given overcast. So here this is 1 and this is 0. So first we do the summation square, 1 square plus 0 square, and then we 1 minus this sum. This is basically the Genie index, right? So this Genie index is equal to 0. So what does that mean? That there is no randomness or chance of you actually making a mistake when you consider this overcast, because it's always gonna be a single class. However, for this case, suppose sunny, the Genie index would be 0.4 square plus 0.6 square. You would add them and then you would minus them from both. So it would be like 0.32. Yeah, it would be a larger value, and this denotes that when you have sunny, there is a chance you would probably make a mistake on predicting the value. So this Genie index, this value, it tries to calculate this metric, and it is very similar to entropy. Like entropy measures uncertainty, Genie index measures the probability of you making a mistake when you just randomly select a class for each feature. And this Genie gain, this is basically the same formula as information gain. You just have replaced the entropy with the feature with basically the Genie index. Okay, so and then the whole algorithm is the same as Id3. So I haven't I'm not going to go through a lot of details for this, because we are going to be mainly focusing on the demos, because you have a datathon coming up, and that is going to be more helpful for you. So in the interest of time, I'm not going to go through the whole calculation. Would be more or less the same as the previous calculation using entropy, just the formulas would change. And then so yeah, and the algorithm is same. You would just be using the Genie index. So if you want the previous whole problem, how it's solved using Genie index, the slide will be available. You can go to the following link. Again, they'll use 20-30 minutes to explain the whole stuff. So, okay. So am I know a lot of you are a bit lost. So am I clear until now about some of the things? Okay, I am going to assume everyone's okay. Okay, someone mentioned in economics Genie index. Yeah. Okay. Yeah, I know a bit. The Genie index in economics, it's a measure of income inequality, but yeah, in machine learning and statistics, it has a meaning of this. And yeah, probably it can be related to the economic sector entropy as well. Maybe, yeah, not sure. Can't give a 100% answer to this. Okay, so moving on. Okay, now a lot of you have if you have like a lot of confusion about Id3, no problem. Just stick to the following slides, because the Id3 algorithm implementation you won't have to do for the data, but the following things will give you a basic idea that can help. So after doing this Id3 algorithm, you have a decision tree. Now, one of the problems of decision tree, which Tanzim probably mentioned in the previous slides, is that there is a scope of overfitting in decision trees. Now, what's overfitting? Now, overfitting is basically the machine learning model, it tries to learn from the training data, right? So during the training data, it has machine learning models have a very bad habit of memorizing stuff. Like learning, you should learn patterns. You should not memorize patterns. Why? Because the problem of memorizing patterns is that when you are given data that is outside the things that you have memorized, you can't you really get stuck and you don't really perform well. Okay, so yeah, it's similar to how humans do. If you're studying on just memorize a single topic, memorize something, and instead of learning the patterns of the stuff, if the questions in your exam are changed a bit, then you start fumbling, because these are not the same things that I've memorized, the same questions or the same content that I have memorized. So machine learning models have a similar thing. So this is basically overfitting. So this decision trees have a very bad habit of overfitting. And in order to reduce this, there are a lot of pruning algorithms that try to that cuts off the noisy or less important nodes of the decision trees. Okay. So there are two types of pruning. One is pre-pruning and one is post-pruning. So the pre-pruning is basically when you're constructing the decision tree, if your information gain at any level is too low, or the Genie gain is too low, you don't expand that node anymore, and you stop. And post-pruning is you basically, after you have generated the whole complete tree, and then you start from the very bottom of the tree, and then you prune the nodes with which has lower information gain, and you go up as like that. So again, these are implemented in the libraries. We don't need to go through you don't need to write code to implement pruning. You have to write code to implement pruning, but you don't need to do it like implement the algorithm from scratch. There are libraries. Okay, now this is quite clear. So this is Tanzim mentioned in her slides as well, that the advantages of decision tree are they're easy to implement, even though it looks quite jarring at this point. But among the machine learning algorithms which can be implemented from scratch, decision tree is the easiest one. And even in using the libraries, it's quite easy to implement. And the classification rules in decision tree are quite easy and clear. Like you have a feature, and this feature has possible values. You basically go down the path using these values. So, and it's clear, and it's sort of called a white box. Now, a white box is basically an algorithm where you can trace each step of the process. Like a sorting algorithm is a white box. At each step, you know what is happening. Whereas, suppose many of you have probably read a lot about it, black boxes, neural networks are black boxes. Neural network algorithms, you don't know at every step what is happening. You can't actually trace. So another positive thing about decision trees is that they're white boxes. And another thing is that they are very fast. They're apart from implementation, when you use them, they give the answer out very fast compared to other algorithms. Now the disadvantages are they have a very big tendency to overfit. Like they will overfit, memorize the training data like crazy. So this is an issue. They have a great tendency to overfit. And suppose if your data set changes a bit, this would cause the whole tree. If you train it on on this new data set, suppose you have 20 new data points coming in, and now you want to train your decision tree on the new data as well. If there's a slight change in the data, like the overall distribution or how the features are, it's going to make your whole decision tree crumble down, and you're going to have to construct a decision tree from scratch. As in, there's going to be a very large change in the overall structure. And the last thing is they do not scale very well when there are a large number of features or the data dimension is high. Like as I showed you, just using 4 features, you have so many calculations. If you have suppose 100 or 500 features, decision trees will break down and it won't perform as well. So the researchers, data scientists have proposed 2 solutions to this problem of decision trees, which is why decision trees are still popular in this day and age. In the day of since our data is very high dimensional nowadays. So these 2 solutions are bagging and boosting. Now we'll be going through this. These bagging and boosting are ensemble methods of decision trees. Now, Tanzim already mentioned that ensemble algorithms are basically, instead of training a single model, you train a bunch of smaller, weaker models, and then you combine the predictions of these models together to find a single prediction. As in, smaller models combined together make a better prediction than a single large model. Now, this bagging is a type of ensemble algorithm. So similar, so this bagging, or sometimes short for bootstrap aggregation, it's an ensemble algorithm where every time you take a number of samples of the data set and use it to train a model, and then afterwards you combine them in an ensemble manner. So suppose you have the original data set, okay? You use a sampling function, or you basically pick at random. So here 8 different data values. You pick 8 different data values from here at random, and then you train a classifier, a small classifier on it. Now this can be a decision tree, can be another algorithm as well, k nearest neighbor maybe. But we since we are considering decision tree here, consider that this classifier is a decision tree. You would train a classifier on this small subset of data. Again, then you will again sample a bunch of get a subset of this original data through sampling, and then train another classifier. And you will repeat this until you have k classifiers. So these k classifiers are actually trained on k different subsets of the original data set. So their classifications, or the things that they have learned, may not be the same. But if you combine them together using some ensembling methods, I'll talk about how this combining works. Then you will have a model that can predict the original data, and it's shown that it performs better. Now it has been empirically shown to perform better by experiment. Many would say that why would weaker models perform better, which are trained on small data sets? But we have shown, you'll see in the demo as well, that it does. So random forest is a special type of bagging algorithm where, along with sampling data rows, like you sample data points, you will also sample the feature columns. Like you won't use all the feature columns every time. So suppose you pick 50 data rows, you would only use out of suppose 7 data features, you would only use 3 data features. So this is a difference. So there's sampling in the x direction and the y direction, in 2 directions. And then after this sampling, or this subset of data rows and features is done, you would train a decision tree on it. And this is done for, again, multiple times together, and then they're combined together to form a single classifier. And this has been shown to this is one of the random forest is one of the most popular decision tree bagging algorithms or ensemble algorithms, and it usually performs much better than the normal decision tree. So now I mentioned that you need to combine these weak classifiers. Now, how do we combine these weak classifiers? There are two popular methods. One is majority voting, as in you when you have a new data, you pass it through all the weak classifiers, and then you have a output class, right? Then one you can do is majority voting, like select the class that majority of these data values, majority of these models say this is the class. So this is the majority voting. And another thing is average. So basically you have the output classes from the different weak models, weaker, smaller classifiers. You basically calculate the average class.
Can you give us an example, please?
Oh, okay. I would need to go to the whiteboard. Okay. Suppose you have a ensemble algorithm. Okay. So C2 and C3. You have three classifiers. Okay. And suppose you have a data feature, you have an input data x1. So based on that, suppose y can take, your output class can be either 0 or either 1. Okay. So for this data value, C1 predicts that it's gonna be 0. C2 says no, this is 1. C3 says that no, this is gonna be 0. This is 0. This is the 0 class. So according to majority voting, your output should be your output should be 0. Why? Because majority of the people are, what happens in a vote? In a vote, you select the majority, right? So among the weak classifiers, most are saying that 0 is the probably one. So yeah, based on voting, you would select 0.
Thank you.
And for average, you basically have so you have 0 plus 1 plus 0, and you have divided by 3. So what, it's 1 by 3. Now this 1 by 3 is probably it's not closer to 1, it's closer to 0, right? The 0 class, you after rounding. So yeah, basically average works like this. You have the average. So am I clear?
Yes, thank you.
Okay. So yes, okay, sorry. So moving on, yeah, this is these are the two methods of combining the classifiers. Now there's the second method of ensembling. This is called boosting or ADA boosting. Now in bagging, you are sampling data every time. Okay, and there's actually no relation between the, suppose, the second sampling or the last sampling compared to the first one. Boosting is different. In boosting, you are the second sample of the subset of data that you sample, it is going to be affected by the very first. Why? So the boosting is such that, suppose you pick the very first subset of the data, you train a classifier on it, and then you see how the classifier performs on the whole training data set. Now it's going to make a lot of mistakes, and you then you're going to pick out those mistake points, and then you're going to give them more weight, so that next time when you sample, values which have more weight are going to be picked. So the values which The data points which the classifier has made mistakes on will be picked more frequently. And then you would train a new classifier that would train on this error-prone values and try to predict them better. But this classifier itself will make some errors. And then, yeah, this repeatedly goes on for n classes. So let me show it visually. I think this would be better. So suppose you have an original data set. You pick a subset of the data, and then you train a classifier on it. And then you test the classifier on the whole training data set, sees performance of the whole training data set. You can see that for this value and this value and for this value, this very first classifier is making a mistake. So what they're going to do is that there are sampling weights attached. Like if your weight is more, there is a higher chance of you being picked when you're using a sampling algorithm, or you, when you are just selecting it, the data point as a in the subset. So the weights of these values, they're increased. Now another subset of values are a new subset of values are picked based on this increased weight, and we train another weak classifier. There's a typo here in the diagram. This would be weak classifier 1. This would be weak classifier 2. Okay, so again you would be training on this, and afterwards this is also going to make a lot of mistakes. This new classifier definitely is. You the points that it makes a mistake on this and this points, so increase the weights of these two, so that in the very next iteration these two values are picked more frequently. And this is done for t times, and then the final classifier, it is a combination of all these data, all these points, and you can see that the performance is much better than actually having a single classifier. So, and this combination is done using average or majority. Now, gradient boosting, this is a special form of boosting algorithm. It's one of the most popular one in Kaggle. Like before neural networks came into the view and everyone started using deep learning, gradient boosting was the most common and the best performing algorithm in most cases when we wanted to do some machine learning. So, and it still has been state of the art for a lot of Kaggle computations, especially where neural networks don't perform that well because there's not enough data. So it's a special form. So where here the weak learners are decision trees, and there's a differentiable function. And here, instead of sampling, your training is done using residuals. So let me just give a very brief background of how decision trees work. Decision trees, not gradient boosting, works. So you have the whole data set. Now there won't be any sampling in gradient boosting. What it does is that it trains a tree 1 on this data set to predict. Now it's going to make mistakes, right? And these mistakes are basically y1 is y1 is the actual label, and minus yi, this is the actually the predicted label. So if the predicted and the actual label are same, then this residual or this error, this residual is actually error, is actually 0. And if it is not, then it's actually going to be some positive or negative value. Now you have a bunch of residual values. So what happens is that now you train another tree, and instead of training it using the X features and the Y output classes, you train them using the residuals. So basically this tree learns to predict the residuals of this, predict the error of this tree. Now this also has an error itself, Rd3. This is going to not predict the residual perfectly. There's going to be some error. So then you train another tree that takes in the input features and the residual or the errors of previous features and tries to predict the errors again. So And this is continued for n times. So what it does is that the current tree tries to predict the error of the previous tree and tries to reduce them or optimize that error, reduce the error. So in this way, the gradient boosting algorithm works. Now, you don't need to, there are a lot of libraries that implement gradient boosting from scratch, gradient boosting. So again, you don't need to worry about implementing from scratch. So yeah, now we're at the end of the workshop almost. I have about 30 minutes. So I feel that it's best now that we do some machine learning code demonstration, because you just only have one other workshop. And after you're done with that, you'll probably have the datathon will be starting, I believe, on this upcoming Saturday. So yeah, so I think it's best that I do some code demos as well. You've seen, you've done some preliminary code demos. Today's one will be a bit more elaborate. So, and most you will be working on Kaggle notebook during your during the datathon. So the codes that I'm going to show are implemented on the Kaggle notebook. So I'll be doing two different demonstrations. The first will be on the Pandas library and the Numpy or Numpy library. So I think during the feature engineering portion of Tanzim, you have seen her use some Pandas, some of the Pandas library functions. Today I'll go into the very basic ones and give you some tutorials on how to do it, because for any datathon or any data science activities, Pandas is very essential to learn. And the second one, it will be on sklearn. Sklearn is a machine learning library that provides a lot of ready-made machine learning models that you can basically train on your data. So you don't need to worry about the from scratch implementation, which I said you don't need to think. Sklearn already provides you with a lot of decision trees. Now, the data set in these demos, we will use the World Happiness Report in Kaggle that exists from 2015 to 2021. So let's begin the code demonstration. Anyone has any question till now? Tasniha Akram. Yeah, we are going to see the coding right now. So anyone has any questions? Okay. So, okay. Let me start with Pandas demo. Okay. Can everyone see my notebook, the Pandas demo notebook that I have opened?
Yes.
Okay. Okay. Let me start my session. Give me a few minutes. 1 or 2. So okay, before this, yeah, first I'll be doing yeah, in this notebook I'll be doing a demonstration of the Pandas diagram. So Pandas is a very widely popular data analysis and management library, and it's used by data scientists around the globe for storing, visualizing, and manipulating data. And I believe that for any data scientist nowadays, learning Pandas is akin to learning Python. Like, if you know, just like a lot of data scientists need to know Python, they also need to know Pandas. Because using Pandas, handling data sets becomes very easy, especially during machine learning competitions like those in Kaggle. Also, at the very end, I'll be doing some a demonstration of the Numpy computation library. So Numpy is basically a Python library that helps to do computation tasks such as manipulating numerical matrices, calculating matrix products or dot products. or finding out the results of any trigonometric or exponential function. It's basically a linear algebra data library, if you are familiar with linear algebra. So let's begin. First, we'll be importing these two libraries. So this is the most popular or common way of calling these libraries. You import Numpy and address it using NP, and you import Pandas and address it using PD. So yeah, let's run. So now this is basically, these are extra code that, okay. So one thing I think I should show is basically you have in Kaggle, it's very easy to load data. Like when you use other methods, you need to download, etc. And then you need to place it in your appropriate folder and such. But in Kaggle, it's quite easy because you have something called, you have this portion of in the Kaggle notebook. So you can add any data set from the Kaggle notebook. So suppose we go to add data here. So suppose we have world happiness. So yeah, see, the data sets are already there. These are Kaggle data sets. Now, if you want to add, suppose you want to add this world happiness report to 2022, you just add it. And then this data set is called in your library notebook. And then what you just need to do is you basically need to go to kaggle.input. You need to go to this folder. Suppose I comment this portion out. If I run this, yeah, basically you will be getting these data sets. So you don't need to worry about like uploading it in the proper folder, etc. This and that. That is doing it on Kaggle notebook is very easy. Now we'll be using, for this demonstration, we'll be using the World Happiness Report 2021. So we'll be going into that folder specifically. So inside that folder, there are two CSV. Well, we need the first one. Okay. So yeah. So Pandas has something called a data frame, and it's basically a data structure of Pandas. In that, this data frame, it can load and store any sort of data set that exists in a sort of a spreadsheet file or in a array manner. Like what happens in arrays? In arrays, you have they are separated by commas. Or what happens in spreadsheet? You have the very first row are the columns, and then each of them are data rows, which are separated by, suppose, colon or comma, or in spreadsheet they're separated by lines. So data frame is a data structure that makes it very easy to load these types of data sets. Now you'll see that in the previous slides, you have also been discussed, like in the database, etc., that your data sets that will be provided, they usually exist in like the very first column or the very first row are the column or the feature names, and then each of them are data rows. Most data sets exist like that. Now loading them using regular Python code, it's quite difficult. You need to open the file, you need to parse, etc., this and that. The data, when you use Pandas and you use the data frame data structure, this becomes very, very easy to do. So this is basically Pandas has a very convenient function that can help us read CSV files. Now CSV is a form of spreadsheet file where everything is separated by commas. Okay, so we want to load this data set into a data frame. So we have the pd.readcsv, and then we have the file. So this basically, we have loaded the data frame. Now, if you want to see the first few rows of the data set of the data frame, then we can use head. So suppose we use df.head. We see the first four. Oh, this is the name of the columns, and we see the first 4 rows. So these are basically the features: country name, regional indicator, etc., generosity, and we see the very first 4 values. So suppose I want to see the first 10 values, then df.head, you just pass 10, it shows the first 10 values. Okay. Now df.tail does that, but from the end, it shows the last few values. So yeah, it basically is showing the last 5 values. So suppose I want to see the last 10 values. We do df.tail this, it will be showing the last 10 values. Okay. So yeah, so moving on. Now I'm going to be showing you some important data frame commands that I find that will be important for you for this computation and for any other data science pursuits that you have. Note that this is not a comprehensive list of commands. Pandas is huge. There are a lot of commands. You can do a lot of things. So I would suggest that you keep on Googling, you keep on searching new things that can be done by Pandas. Like if you have any queries like, can Pandas do this? Suppose you have a query like, can Pandas can Pandas calculate the histogram? Or can Pandas calculate the 25% quartile? Just Google it. I'm pretty sure, 90% sure, Pandas probably can. So Pandas data frame specific. So yeah, let's see the. So we have the first this. So df.columns. This basically gives you all the column names that are there. So basically these things. Then you have df.dtypes. Now I believe that in the previous workshops you have went through a bunch of examples of what data types can exist. It can be floats, it can be integers, it can be objects, it can be strings, so etc. So in Pandas there exist data types as well. So this is basically the df.dtypes. It basically shows you the data type for each column. Like for example, the first 2 are basically strings. They're strings. So in Pandas, strings are defined as objects, and you can see the rest of the columns are basically values, numbers, specifically numbers. I mean, and they are floating numbers, as in they're not integer numbers. They are rational numbers with decimal points, etc. So yes. Okay. So yeah. So these are the data frame.dtypes. So this is the thing. So and then there's something else. This is a very interesting function of Pandas data frame. This df.describe. Now what it does is that it basically for each of the numerical, it cannot do it for the non-numerical columns. Each of the numerical columns, as in the integer columns or the float data type columns, it calculates a bunch of the matrix that has been discussed, like a bunch of statistical metrics, like the count, how many values count, basically how many values are there, the mean of this column, the standard deviation of this column, the minimum of this column, was the 25% quartile, was the median, was the 75% quartile, was the maximum value, etc. So it basically calculates this. So you don't need to calculate it like on your own. Pandas basically gives you all these metrics and lets you visualize it all at once in a data frame data structure. Okay, so yeah, and then there's suppose there's something called okay before I come to this, let me go to this. this column. So there's now how do we access, suppose in data frames, how do you access the 148th row, or how do you access only this column? Now accessing columns in Pandas is very easy. So suppose let me do a df.head again so that we don't need to move multiple times. So suppose you want to access the perceptions of corruption column. You want all the values in this column. So you just do this indexing. You just write in the index, you write the name, and you can access the perceptions of corruptions column. It's that easy. See, it gives you all the values. So, however, suppose you want to access multiple columns. You want to access ladder score, you want to access social support, and you want to access generosity. In that case, you would need to write a list of the arrays, and you would have to put them inside. Okay. Here, you since you're just calling one column, you can just write it like this. But when calling multiple columns, you need to put another brace in and index it like this, and then you put the commas in and the column names that you want, and yeah, you would have the multiple columns. Now suppose I don't want the columns, but I want to access the rows from which start from the index, like this in Pandas is the data frame is the index. You want to access the indexes, index 10 to less than 20, as in 90. So what how do we do it? You can't do it like in you have done it in Python slicing or basic Python base. You would need to call in something called .loc, and after that you would basically need to mention the starting index and basically mention the ending index plus 1, just like a Python list, but you would need to call lock. So in so here, yeah, I've done basically that. So it calls in 10 to 20. Okay, so yeah, okay, you don't need to call the n, it will call in the 20th value as well. So if you call in 15, it will display to you from index 10 to index 15 the values. Am I clear till now? Hello?
Yes,
you are.
this is very
Thank you.
helpful.
Okay, okay. So okay, and now let me go to this. Now this is suppose you know indexing, right? So suppose you take in the country name, you consider the country name, and what value counts does is that it sees how many unique values are there in this column, and then it mentions how many times this value is repeated in a column. So obviously in this data set, each country has only one row. So basically it will give the country names and how many times they exist. They exist only once. But suppose you have in the column, it's like a date between, you have 1,000 rows, but you have a date that's between value that's between 10 and 20. So each of these values are going to be repeated a bunch of times. So value counts will basically show you how many times these are repeated. So yeah, this is basically what value counts does. Now this is another interesting function. Now what this function does is that this drops duplicates. Suppose you have the same row multiple times in your data set or data frame. Drop duplicates. This once you implement this line, it will basically replace the duplicates and keep only the single one. Now, mind you, even if there is a very tiny fraction of difference, it will still it won't drop. But if it's the very same, like in every values they are the same, then it will definitely be dropped off. So in this data set, there's no duplicate, but in your data set there might be. So one way to drop duplicates is to just write this line. Okay, so there are some other values. So another thing is that I think maybe in the previous workshops it's been mentioned, like in your data frame, there will be times when you will have null values. As in, suppose you have this data set. Suppose for this row, the freedom to make life choices, you don't have any values for it. It's a null value. Like it wasn't. Maybe it was the error when noting down, creating the data set, or maybe they didn't have this metric. So there can be data nulls in data sets, and you cannot use like for calculating metrics and such and using in machine learning algorithms, you cannot use that data set when there are null values in. So first thing is, how do we check whether there are null values? So there's this function .df.isNull.n. Now this basically says for each column whether there's a null value, like if there is a null value in any of the columns here. Okay, so this is one way to check whether a column has a null value. Now there are one way of eliminating null values from your data set is to drop that whole row altogether. Like suppose in this case, if the freedom to make life choices, this has a null value, you drop this whole row altogether. So this can be done using df.dropAny. So yeah, this will drop any rows which has any null values in it. Now another way of doing is to like fill the null values with some representative values. Now this can be 0. I think it's been discussed. This can be also the mean of the column itself, etc. So this can be done with df.fillNA, and then you pass the df.mean. The df.mean basically calculates the mean of each of the columns in the data frame. And so if you write this is going to replace the null values that exist in any of the columns, in any of the data rows, with the mean. So yeah, ignore the warning. Okay, and this basically sorts the data frame by a suppose one column. So suppose I want to have the data set sorted by the country name, it will do that. So basically, yeah, it's sorted like this. And now suppose this is an interesting function. I don't expect you to understand this now, but it's you will have to use it a lot during data science. So there's the function called group by. So what group by does is that it takes in a column name and it groups all the other values according to the values of the column. So suppose I provide group by with we want to group by the regional indicator. Now regional indicator has suppose 10 values. So what happens is that this whole data set is then grouped together or arranged such that it corresponds to each of the regional indicator values. Like first will be the South Asia, first then will be the Central Eastern European, all the Central and Eastern European values, etc. Now, why is this interesting? Like when you have this data frame grouped by a certain column, then you can find the corresponding matrix for other columns corresponding to the first. It's like almost like the database, during if you've done SQL, it's like joint conditionals. Yeah, I'm pretty rusty on SQL myself. So yeah, it's something like that. So it's basically so the df.group by the freedom to make life choices. So first we group it by the regional indicator, and then we want to measure the median values of the freedom to make life choices. So what it does is that, yeah, it shows basically the median values for this column based on the values of the regional indicator. So I don't expect you to know group by right now, but know that this, but just keep it in your mind. Okay? You'll easily know you will be able to use this later on. So yeah, I've mentioned a lot of Pandas tutorials. This is not comprehensive at all. I've just shown you a bunch of simple functions. So there are a lot of Pandas tutorials out there. I've mentioned a few. You can go out there, and if you have anything related to Pandas that you think, is it possible? Just Google. Like if you ask people, they might say that it's not possible, this and that. If you Google, you'll find the answer. So, okay, this I'm going to go through very fast. I think a lot of you know Numpy or NumPy, whichever term you prefer, both work. So NumPy is basically an computation library. So suppose you have a list here and you have the NumPy array here. You can convert this list into a NumPy array. Now, in terms of representation, a NumPy array does not have any commas in it, while a list does. Now, NumPy arrays enables arithmetic operations which are not possible on lists. Suppose you want to add all the 1 to all these values. This is not possible in traditional list. It will give you an error. But if you do it on NumPy array, this is very easy. Okay, so yeah. Now, NumPy allows a lot of wide range of operations on it. So suppose the original array X is 10, 20, 30, 40. You can add 1 to it, deduct 1 from it. You can multiply it by 2, a scalar value. You can divide it by a scalar value. You can even calculate the power of each of the values. And another interesting thing that's possible is that it provides element-wise multiplication. In that, if you have 2 NumPy arrays and you just multiply them together, so what it will do is that it will basically multiply the corresponding values. Okay, so basically 10 is to 1, 20 is to 2, 30 is to 3, and 40 is to 4, and you will get this value. Yeah, it's yeah, sorry, this one. It's that simple. And then you can have matrix multiplication, as in you can multiply them in a matrix manner. So yeah, you if we do multiply x with x itself, then it gives this value. And if we multiply x with y, matrix multiply x with y, gives this value. You can do the hand calculation later to see that this is true. Okay, now Numpy also provides a number of inbuilt functions for number of tests, such as it can you can calculate the transpose, the exponentiation, the mean standard deviation of an array. You can calculate the mean across each of the dimensions. So if you give the axis 0, it will calculate across the rows. If you give the axis 1, it will calculate across the columns. So here the mean is calculated across the columns. So yeah, it's 10, 20, the mean is 15, and 30, 40, the mean is 35. So 15 and 35. You can calculate the mean, max, and reshape is basically it can change the shape of the array itself. Suppose we want currently the array is 2 by 2. We want it to be 4 by 1. It basically reshapes the array. And yeah, we can calculate the log of each of the values in the array and the square root as well. This is again a non-comprehensive list. And it can also help generate random numbers such as np.zeros. If you give the size, you can get a 2 by 2 matrix of the zeros. You can also get a 2 by 2 matrix of ones. Now, if you want to have a random normal array, so you can say the mean, which is the log, the scale is the standard deviation, and what size of the array do you want. Then it will give you a normal an array of size this, where the values are sampled from normal distribution. And you can have also arranged values where suppose you give the starting index and the ending index and the step size. Then it will generate from this to less than this. And each time it will like change it. The values will be changed to this. Okay. So each time this increase like this. So 0, 2, 4, 6, etc. Okay. So NumPy has also a lot of easy indexing options. Like suppose you have a 4x4 array. You want to select rows 1 to 1 to less than 3. So these two. This can be done like this. Suppose you want to select the last two columns. You just write it, do this portion, write like this, and then say 2 to 4, and then these two columns are given. And suppose you want to select from the middle two rows the last two columns, and then you write it like this, 1 to 3. You select the rows and then you select the columns, and it gives you that portion. So I've barely scratched the surface of Numpy. There are thousands more operations that you can do. Some resources are mentioned here. So I will be taking just 10 more minutes. Okay, so it will be 5 minutes more above your current time to just show you the model demo. Is there any problem with anyone? If anyone wants to, does anyone have any problem with what I've shown till now?
No, all good.
Okay. Okay. So yeah, I'll just take 10 more minutes. So this is a model demo. Now this is on the sklearn library. So sklearn is basically a Python library that provides a lot of ready-made inbuilt functions. Functions which can be called to train a machine learning model. So you want to train a linear regression model or decision tree, or even a random forest or gradient boosting classifier. You just call that these functions. So you just call this library, and there are functions in it that you can call. So first and foremost, I'll be so yeah, let me start off with the session. Loading the session. So okay, while this session loads, so I'll be importing the libraries. We have the Numpy and the Pandas library. Okay, the data set has been loaded. Folder. So here we'll be using the data sets from 2015 to 2019 of world happiness. So okay, so first I'll be importing the libraries. This is a matplotlib library. You don't need it at this point. I'm not using it for any purpose. So okay, yeah, see sklearn. So these are specifically, I'm loading the linear regression model, the decision tree model, and the random forest model, and the gradient boosting model from the sklearn. Now, if you want to know how do I load this model, what are the libraries, just Google sklearn, this model name. There, it will direct you to the sklearn documentation page. You can just search it from there. Okay. So, and these I'll show later. This is basically classification report. It calculates for classification tasks. It gives you the F1 score, the accuracy scores, etc. If you just pass your predictions and the actual values. And this matrix is basically calculates the accuracy. If you give the prediction and the actual values, output values plus, it will calculate the accuracy for you. Now these are helper functions. This calculates the root mean square. This calculates the mean average error, and this calculates the mean average percentage error. You can look this up online. These are just to help you out. There isn't anything special about these two functions. They just take in the actual y values and your predictions. Prediction values. Okay. So now I'll be loading these libraries. Okay, they're loaded. Now this portion, you don't need to think about it. You can look through it in your free time. Basically, what I'm doing is that I'm combining all these are five different data sets. I'm combining them together to form a single data set. And the thing is that in this data set, there's no classification. There's nothing to classify. It's all linear regression values. So the class is actually it's a regression task. So I converted it into a classification task basically. So you can look through it in your free time. There's nothing much here to describe. So, okay. So yeah, if I just look through the data set, it basically shows you have the country, you have the happiness score, you have the economy, GDP per capita, family, freedom, trust, generosity, year, and is happy. Now the regression task is given this from economy to generosity. You have these columns. The regression task is to predict the happiness score, and the classification task is to predict is happy, because there are two values. It's a binary task: is happy or isn't happy. Okay. Now, Pandas provides a unique way of visualizing the histogram of the values, how the values are distributed across each column. So this is a function to do that. So it basically is showing how the values are distributed. It basically shows the histogram of each column. So okay, now our regression for the regression test, we'll be using this will be our output class that we'll be predicting, and we'll be using economy, family, health, freedom, trust, generosity as the input features. We won't be using the country name. And the for the regression, the training data sets are all the values from the years 2015 to 2018, and the test data set is from the year 2019. Okay, so yeah, we basically take all the values which are in 2019, the year is in 2019, and then we remove the null values. You don't need to convert them to z-score. We're not doing that. If you are familiar with z-score, you can do it. It's very easy. It's very easy. It's basically this line, but I am not sure whether this is in the scope of the lectures. So yeah, first we are removing the null, and this is basically we are removing the null, and this is basically shuffling the data. Like you're aware that we should shuffle the training data, like mix and match it up, or else there could be a chance of overfitting. And then we take, yeah, for the training input we take these columns and the out, and then there's a neat function called toNumpy that converts these pandas variables into Numpy array, pandas data frame to Numpy array. Okay, so and similarly we're creating the test data, and we have this. So yeah, okay, there's nothing much here to say. Okay, it's done. So yeah, now we are going to train a linear regression model. So previously we've called the library function for linear regression. Now you just need to write this function name, linear regression. It has a lot of arguments inside it. I'm not using any specialized arguments, but there are possible, like how fast it will do, how many, what will be the error, etc. There are a lot of parameters there. Just go to the sklearn documentation and you can see them easily. But basically, first you initialize the model, then you write something called fit, and it takes in the input as x train, and it takes in the y train, basically the x and y pair. And then you would want to perform prediction. So for that, you call the model's predict function, and you call it on the x, the test input features, x. And then these are the functions that I already wrote, RMSC, in order to measure the regression values. Okay, someone said, will we get good output? You will get better output with z-score. Currently for this data set, I've seen that you are getting a decent output without z-score, but you will definitely get a better output with z-score. This is this code will be given to you. You can implement it with z-score and see how it performs. So yeah, these are the basically the metrics which are calculated. So let's run it. Okay. Yeah. So you can see the errors are quite low. It's only 8.76, less than 10. I mean, absolute percentage error is quite good. And the roots mean square error and the mean absolute error, they are also quite low and close to each other. So this is a good thing. So yeah, this is basically how you can use this code snippet in the datathon or in any place that you want. It's more or less the same. Now, just like I've created a regression test, so I'm creating a training data set and testing data set for the classification test. There's not much difference except that we're using, sorry, the is happy training data, is happy column as our prediction. So here again, the values, nothing is actually that different. So first we define the model decision. This random state, this is just an argument. Random state usually is a seed, if you are familiar with seed, or it basically makes sure that it's a input variable, input to a function that the model function that makes sure that every time you train the model, it does not give you a random model. It gives you a sort of fixed train model because there is some randomness inside models. So it acts as a seed. So there are other things as well. Again, go to sklearn and look through them. And then there's these three lines are very similar to the last regression one. Now we have the class names are not happy and happy. So not happy is equals to the zeroth index, and happy is the one value, so the 1th index. So okay, the classification report, this is a function in sklearn that basically if you provide the actual values and predicted values and you provide the class names or the target names properly indexed, it gives you everything, the F1 score, precision, recall, etc. And this is basically an accuracy score. It basically calculates the accuracy, and you have to set it to normalize close to 2. So basically, yeah. Oh, I didn't run this. Yeah. So yeah, you have the values here. So you can see the everything, your accuracy and everything. So you're getting about 86% accuracy on decision tree. The random here we have the random forest, basically the same thing. Max depth is just another random forest argument that it will just create weak classifiers which has a depth of 2 or only consider two features. Up till then it breaks up. So there are other as well. So again, if I train it here, you can see that here the accuracy is 87%. I told you that random forest is better than normal decision tree. Since this is an easy task, the decision tree performs well, but you can definitely see that random forest has a higher accuracy. It has 87% accuracy. And finally, we have the gradient boosting classifier on the classification data set. The same code here. These are a bunch of what can I say, values, arguments for the gradient boosting classifier. You can look through them, which are what. I can just say that this is the learning rate. This is the maximum depth of each of the gradient tree. And n estimators means how many classifiers will be there. So there should be 100 weak classifiers if you consider that. So this is basically that. There are also other arguments. Just I'll show you then how to look for them. So yeah, let me train this. And you can see that the performance here is there's a 2%, almost 2% increase. It's like 88 or 89%. So yeah, again, I told you that gradient boosting is better than random forest. So here I did that. So these codes are more or less the same. So yeah, I've provided some links that will help you to learn how to use models in sklearn. And as I said, suppose you want to learn sklearn, you want to use what model? K-nearest neighbors. So yeah, If you just search this, you'll have the details here in the documentation, and you can know which parameters are what. Okay, and there'll be a small code snippet on how to use this. So yeah, I talked a lot. I think yeah, we can end our meeting here. If anyone has any questions, any questions?
I just want to tell everybody, please keep on registering for the datathon. I have created an announcement channel on this Discord server, and also there is a looking for a team channel. So if you're still single or still looking for teams, please look for teams on Discord channel, and please register as soon as possible. And otherwise, we will see each other again on Friday with Carolina. She will talk about evaluation and validation, and I'll give you some idea about time series prediction.
Okay. Oh, okay. I guess. Yeah. I'll. And okay. Tanzim, can you end the meeting then?
Yeah, I think the host will end it. Yes, thanks, Saqib, for joining. It was a really great session. Thanks a lot. And we'll see you soon. Host, can you please end the session? We're done, I think.
Thank you, everyone. Yeah,
Okay.
the slides and the code will be posted over there. Thank you.
Thank you. Bye.
Bye.